Yes, good. All right, so I'd like to introduce Sebastian Gold, who will be giving the oral for the start of the session. It'll be on SG dynamics for two-layer neural networks in the teacher-student setup.
Thank you. Thank you for having me and for giving me the opportunity to present some of the recent work that we did together with Madhu Advani, Andrew Sachs, Florent Jacala, and Lenka Steborova. And the motivation for this work was to get a better understanding of why overparameterized neural networks perform as well as they do in practice. And our idea was to look at this problem using the teacher-student framework of statistical physics. The key idea behind the teacher-student framework is that you generate a data set by feeding random IID inputs through a random neural network called the teacher. And here we're going to take a two-layer, fully connected neural network with some activation function G in the middle. And for every IID input X, its true label is going to be the output of that teacher network with some additive Gaussian noise of variance sigma. And then you take this data set and give it to another two-layer neural network called the student. And you train the student on that data set by doing vanilla SGD on the quadratic error. And we're going to look at this model in the limit where we take the input size very big, but we keep the number of hidden nodes in the teacher and the students of order 1. The key quantity for this study is the generalization, or the test error. And we define the test error as the mean squared error between the teacher and the student output averaged over the input distribution. And so we wanted to understand, how does this test error at the end of training depend on the amount of overparameterization in the student network. And here we're going to define overparameterization as the number of additional nodes in the student compared to the teacher. Now that's a bit different from other studies which commonly define overparameterization by comparing the number of parameters in your model to the number of data points that you have in your training set. But a priori for nonlinear functions like a neural network, this parameter counting is not really justified. And so here instead we're going to say the student is overparameterized if it can implement a more complex function than this teacher can express. And so our question was, okay, how does the test error depend on this overparameterization L? And rather than trying to get bounds on the test error, what we did is we looked at the dynamics of the student and tried to use that as a tool to gain some insight. In particular, we looked at online SGD, so that's just plain stochastic gradient descent, where at each step of the algorithm, you have a new sample with which you calculate your gradients. And you can put that into a computer, you can run that algorithm, and you can plot the test error as a function of time. And what we want is sort of some analytical control over that quantity. And the key idea to get this is an idea that's been around in the statistical physics literature for some 20 years or so, and that's that actually, if you want to calculate something like the test error, you don't need the full microscopic detail of your setup. So you don't need to know all the weights in your student, all the weights in your teacher. What you really need is only a couple of quantities, which are called order parameters in physics. In this particular case, the order parameters that you're interested in are your second layer weights and quantities that we will call the overlap, QRT. And to give you some intuition on these overlaps, basically what they do is they measure the correlation between the weights of different nodes in the teacher and the student network, okay? So for example, if I take the teacher-student overlap R12 to be precise, well, that's going to be the correlation between the first weight vector of the teacher and the second weight vector of the student, okay? And the intuition here is that in the beginning, these are high-dimensional objects, IID random variables, so clearly, almost surely they're going to be orthogonal to each other, and this overlap is going to be 0. But then during training, hopefully what will happen is that the student picks up some of the structure in the teacher, and so that its parameters get correlated to the teacher parameters. And then this overlap will increase, and knowing this parameter will then allow you to calculate the test error. Now, you can express the test error in terms of these overlaps, and that's a useful thing because what people showed in the 90s, Sarden-Sola and Biel and Riegler, is that all these order parameters, they obey a closed set of equations of motion. They're first order ODEs, so you can just integrate them, look at the values at any point in time, and that will allow you to calculate the test error. And that's going to be the tool that we use in this work. Let me just say that our setup is somewhat complementary to some recent work on two-layer networks that appeared around the same time last year, where people looked at the nonlinear PDE that governs the dynamics of the weight distribution. And also they looked at a slightly complementary limit, so they took the hidden layer to infinity while keeping the input layer of order 1. Now, the two contributions of our paper are first the mathematical result. We prove that the ODE description that was conjectured in the 90s is actually asymptotically correct. And then we have some what we call physical results, where we actually use these ODEs and try to extract some information about them and try to calculate the test error. Before I jump into these results, let me just quickly give an informal statement of our theorem. So, assuming that the sequence of inputs and the sequence of teacher noise are IID random variables, and together with some technical assumption, we have the following statement in the thermodynamic limit. The expected difference between the order parameters that you find from actually evaluating the correlations in a simulation and the order parameters that you find from integrating the ODEs decays as 1 over the square root of the input size. Okay, and as I said before, we take the input size to go to infinity. You can prove this using some standard concentration arguments together with a coupling trick that was recently introduced by Wang and co-authors. And the gist of this theorem is shown in this plot. Okay, so here again, I'm showing the test error as a function of time. The solid lines are what you obtain in the simulation, and the crosses are what you obtain for the test error when you integrate the ODEs. And you can see that they match pretty well. And now that we have this tool and that we know it's rigorous, we can use it to actually learn something about neural networks. The first case that we're going to look at is a network with a sigmoidal activation function, where you train the first layer only. Okay? And our goal will be to calculate the test error at the end of training. So what actually happens during training? Let's take an example. Let's take a teacher with 2 nodes and a student with 5 nodes. And for the moment, let's assume that there's no output noise in the teacher. Okay? So in the beginning, there's no correlation between the random initial weights of the student and the weights of the teacher, which are also random. So something like the teacher-student overlap matrix, it's just going to be 0 everywhere. Right? Now, as you continue training and as you iterate training until the end, what's going to happen is that 2 of the hidden nodes of the student, they're basically going to learn the weights of the corresponding teacher nodes, whereas the weights of all the other nodes will go to 0. And that's a pretty good configuration for you to be in, because then you have a test error that's 0 and you're all happy. Now, if we turn on the noise in the output of the teacher, the test error will be non-zero. Obviously, we want to calculate it. And our idea was to say, well, okay, let's take this 0 noise fixed point with perfect generalization, and let's expand around it. Okay, so let's look at the perturbation theory in the noise and see if we can calculate the test error using that. And indeed, you can carry out this program, and you can get an analytical expression for the test error for any m, any k. It's a pretty long expression, and so instead what we're going to do is we're going to show you a plot. Here you see the test error of the student as you make the student bigger. And what you can see is that the solid line, which is our theoretical prediction, and the crosses, which is what you see in experiments, match pretty well. The second thing that you will note is that actually here the test error increases as a function of student size. Now that's a bit counterintuitive, because we've been sort of trained to say that, okay, the bigger your model, the better you're going to generalize. But you can get some intuition for this result by, again, looking at the overlaps. Okay, and in particular, if you think about the configuration that we had for 0 noise, now if you have some output noise in the teacher, what's going to happen is that the correlation between the teacher and the student nodes goes down, and then furthermore, you're going to have some non-zero weights in the other nodes, and they're just going to contribute noise to the output of the student, and that's going to deteriorate your generalization. Okay, and this intuition is actually borne out. If you expand our analytical result for small learning rates, you can see quite neatly that there's a term that's proportional to the number of superfluous units in your student, and that diminishes your test performance. Now, you might think that actually this result is just an artifact of the specialization, and we wondered about that too. So it's useful here to look at linear networks. Linear networks because they have no specialization transition. All the student nodes have correlations with all the teacher nodes. You can carry out the same program, and what you're going to find is that, again, the error of the student is going to increase with its size. So this seems to be like quite a generic effect, and we also confirmed this numerically for networks that have a ReLU activation function. Now, things actually change quite drastically if you train both layers of the network. So going back to the case with the sigmoidal activation function, again, if you plot the test error as a function of student size, you will see that it goes down. In some cases, you can actually exactly calculate it, and it's a 1 over k decay. And so what's happening here? What has changed? Again, the overlaps are quite instructive. What's happened is that the student now uses all its hidden nodes, rather than just trying to shut them down and let their weights go to 0. Indeed, what it does, it basically makes several copies of the teacher network, and then takes an effective average. So it's sort of averaging out the noise with the additional parameters that it has, and that way generalization error can go down. We also looked at the linear networks when you train both layers, and actually in this case, the simplest case is a bit more complicated. If you just train both layers of the linear network, you'll find that the error stays flat. It stays constant. I mean, that's not very exciting, but it actually makes sense because there is no specialization in the linear networks, so you can't really do this model averaging in a linear network as easily. What's maybe more surprising is that if you train only the first layer, but you clamp the second layer weights to a fixed value, in this case 1 over the number of hidden nodes, the error actually goes down as you make the student bigger. So this is then an example where actually stochastic gradient descent, when you train on both layers, it doesn't find the optimal solution starting from small initial weights. And instead, there's a better solution than the one obtained by SGD, but somehow it's hidden in the landscape, and SGD doesn't get there, at least not in finite time. Now, let me just conclude by saying that analyzing the dynamics of neural networks yields many insights into generalization, and we've seen that here in our model, understanding generalization, it really requires understanding the interplay of both the optimization procedure and the architecture. So which activation function do you use, which part of the network do you train? But at least in my opinion, I think there's one piece that's still missing here in the puzzle in this model, and that's better models for data structure. If you think about most theoretical work, what they do is they either take no assumptions on the data at all, or they assume that inputs are just some IID random variable. So by construction, these approaches are blind to the structure that's present in real data sets and to the impact that that structure might have on the performance of a neural network. And so we recently attempted to take a step at closing this gap between theory and practice by proposing something that we call the hidden manifold model. We're pretty excited about this, and if you want to learn more about this, there's going to be a talk and a poster at the Science Meets Engineering workshop on Saturday. Thank you very much.
Hello. Good. Hey.
Sorry, give me 1 second. So
Sure.
thank you for already asking a question, but can the spotlight presenters also line up? And then, yes, please ask questions.
Yeah, could you just explain us those two plots you have on there again? Because I think it was hard to see which lines you were referring to during your talk, unfortunately.
Sorry, which lines of which plots?
The plot on the top right and the
Yes.
one below it, maybe referencing like the colors, because I really can't see like which ones have crosses or solid lines and stuff like that.
Okay, so okay, sorry about that. So basically, in the top right plot, that's where we compare simulations to the ODE theory. Okay, and all the lines have crosses in the same color, and so if you don't see them, I hope that convinces you that actually the match is pretty good.
And the one below?
And the one below, so that's that's for two different teacher sizes in orange and in blue. The generalization error of sigmoidal students, that's the two bottom curves, and linear students, that's the top two curves. When you train only the first layer, and you can see that the error goes down as a function of goes up, sorry, as a function of student size.
And orange versus blue is just two different like hyperparameter settings or something?
It's two different teacher sizes.
Oh, okay. Thanks.
Cheers. Another question?
Any other questions?
Well, thanks a lot for the inspiring talk. I was wondering, when you compare now your teacher network or let's say the correlation between the weights in your teacher and your student, and you don't have a high correlation, could it still be that you learn a correct function that is just, or the same function that is just parameterized differently? Is that still possible, so that your generalization error would still be low?
I'm not quite sure I just acoustically understood the question. So if you start from different initial conditions,
Yeah.
it can happen that you learn different functions in the sense that, microscopically your weights are not going to be exactly the same. You might have different patterns of specialization. That really depends on the initial conditions. But these macroscopic quantities, like the test error, for example, they're going to be consistent from one run to the next. That's a nice thing about having these macroscopic quantities.
Okay, thanks.
Yeah, we still have time for maybe one more quick question.
So I'll ask another one. when you didn't have any noise, you said that if you have 2 nodes in the teacher and 5 in the student, then you'll have 2 of the nodes in the student that will just learn to match the ones in the teacher. But like, couldn't you just end up spreading the same computations over multiple nodes as well? Or is there a reason that it necessarily will put all of those computations in just 2 of the 5 nodes?
That's a really good point. So that's exactly what happens if you go from training just 1 layer to training 2 layers, right? When you train 2 layers, the student basically makes several copies of the teacher model and then takes an empirical average. So it's sort of doing model averaging, which is quite surprising if you think about that. It's been just trained using plain SGD, right? Doesn't know that there's a teacher, doesn't know how many parameters it has. So if you train both layers, that's exactly what's going to happen.
Thanks.
Let's thank the speaker again, and we're now going to have a sequence of spotlights without questions.
Thank you.
Hello, I'm Surbhi Goel, and today I'm going to be talking about the computational complexity of learning a single ReLU unit on Gaussian marginals. This is joint work with Sushrut Karmalkar and Adam Clivens at UT Austin. So what is the problem that we're trying to address? So here we're going to talk about ReLU regression. This is a really simple model where you have input data and you're trying to fit the best possible ReLU to your data in terms of squared loss. So more specifically, you're given samples from some underlying distribution D, and you have arbitrary labels. So your labels could have any kind of noise. They don't need to come from a specific ReLU or as such. And our task is to output a ReLU such that the test error with respect to squared loss is competitive with the best possible ReLU that could be fit on your data up to error epsilon. Okay, and the challenge that the underlying problem has is that this problem is highly non-convex because the ReLU is inside the squared loss, which makes it a very challenging. A lot of work has been done in this area, and I'll highlight some positive and negative results. So on the positive side, if you assume that the noise in the label is mean 0, then in fact there's a line of work which distribution independently learns this problem. And in the noiseless case, in fact, if you assume the input is Gaussian, then gradient descent in fact can get to the optimal solution. Note that these results either require that your label has structured noise or your distribution is very specific. However, something like this is necessary by the negative results that are known. So in fact, minimizing just the training loss, not even the test error, is NP hard. And if the distribution is uniform on the Boolean cube, this is actually known to be computationally hard. However, these results require these special discrete distributions to prove hardness, which is not common in the data distributions that are used. So our result focuses on the distribution, which is the Gaussian input distribution. And the reason we assume this distribution is because this has led to a lot of positive results in noiseless settings, and a lot of work has shown that, in fact, if you make this assumption, you can show that shallow neural networks actually learn the models. However, we show that, the reason that they're able to do this is because of the Gaussian input distribution. You can explicitly compute closed form expressions, and this makes us easy to analyze the trajectory of gradient descent and other algorithms. However, we show that, in fact, there is no algorithm for doing this problem up to error epsilon in polynomial time under standard computational hardness assumptions. More specifically, if your dimension is d, then there's no algorithm that runs in time d little o of log 1 by epsilon. And this problem is as hard as learning sparse parities with noise, which is considered a computationally hard problem. This is the first result that's known under the Gaussian input distribution. Furthermore, we can show that, in fact, no SQ algorithm with bounded norm queries can perform this task up to error epsilon with queries that are d to the little o of log 1 by epsilon. It's well known that gradient descent, in fact, is an SQ algorithm, which implies that gradient descent cannot solve this problem in polynomial time. Recall that I mentioned that gradient descent works in the noiseless setting. So this problem becomes very challenging if I'm allowed to add any kind of arbitrary noise to my label. But this makes it seem like all hope is lost, that you cannot even solve this simple problem. How do you hope to learn neural networks? In fact, we do show that if we weaken our guarantee that we do not want to be competitive with the best possible ReLU, but we want our error to be within some function of the best loss, then in fact you can do this in polynomial time. So here we can get opt to the 2/3. Think of opt as something less than 1. So we're not able to get the best possible, but close to that. And in fact, in subsequent work, we can show we can actually get order opt, so a constant opt solution in polynomial time. This says that, in fact, finding approximate solutions is tractable, and in most tasks, maybe we do not care about the best possible solution, but a good solution is good enough. If you find this talk interesting, please come by my poster at poster number 235. Thank you so much.
So, hello everyone. So my name is Theodor Miziakiewicz. I'm from Stanford University, and I'll be presenting my paper on limitations of lazy training of two-layer neural networks. So this is a joint work with 3 amazing people, Behrooz Korbani, Song Mei, who is somewhere here, and my advisor, Andrea Montanari. So, yeah, sorry. So as hinted in my title, we consider a two-layer neural network and a particular training regime that has attracted a lot of attention in this past year and called lazy training regime. So in this regime, the parameter theta t learned by gradient descent remains very close to their initial value, theta 0. So we can do a first-order Taylor approximation of our neural network. And when we expand this linear term, we get 2 linear models, and I'll refer to these 2 linear models for the rest of the talk as like random feature model, null tangent model. These 2 models are related to the null tangent kernel that was presented yesterday by Ruasang Wang. And so just a bit of details. So like the WI0 are random weights fixed at initialization, and we only feed the parameters Ti and Bi. So a lot of work has been done comparing this fully trained neural network on the left-hand side and this linearized neural network on the right-hand side. And the high-level question is, can this lazy training picture explain the success of deep neural networks? So we asked 2 related questions. Do random feature and null tangent model provide a good approximation to effectively trained neural networks? And second question, do random feature and null tangent models learn good representations of the data? So here's the setting. So these 2 questions are fairly difficult, so we decided to look at a simple setting where we could fully characterize the behavior of these 3 models. And in this particular simple setting, we were able to show that these 2 questions admit negative answers. And here's the setting. So we take isotropic Gaussian data, we fit a quadratic function with matrix B, we track squared nonlinearity, the neural network is trained by SGD, and we compare the population squared error loss. Here are the results. So we plotted the normalized risk against the number of hidden units, n. The lines are analytical predictions obtained in the paper, and the dots are empirical results. So like this first black line is the result for the random feature model. And so as you can see, the random feature model does not fit the quadratic function, and this remains true regardless of the nonlinearity chosen. Here's the result for the neural tangent model. So the neural tangent model will fit the matrix B along random directions spanned by the random weights WI0 fixed at initialization. And here's the result for the neural network trained by SGD. And so here, the NN model will fit the directions of B corresponding to the highest eigenvalue of B. So what we were able to prove is that, first of all, there exists an arbitrary large gap between the neural network trained by SGD and the null tangent model in this particular setting. And the high-level reason is that the neural networks are superior to linearized models such as RF and NT because they can learn a good representation of the data. And here, a good representation of the data is like the most important again directions compared to just random directions. And you have like further results in the case of mixture of Gaussians, ReLU activation in the paper. And so the main takeaway of this work is that we should exercise caution when looking at the lazy training regime and linear neural network. And so you can come discuss with us at our poster. So poster 230. Thank you.
Just a quick question. So is either Amit Danieli or Elad Gurnell here, the spotlight? If not, we will be skipping the third spotlight as no one is here to deliver it. So we'll go directly. Come up, yeah. Just click through. Oh, is this you?
Yeah. Oh, yeah.
This one's you? Yeah. Okay, good. Go ahead.
So, hi, everyone. My name is Charlie, and today I'm going to be talking about our paper on the memorization capacity of ReLU networks. And this is joint work with my advisors, Suvrait and Ali. So the question we consider in this paper is, given a ReLU network, how many hidden nodes are required to memorize arbitrary n data points? So it's well known that overparameterized neural network can memorize even random noise, but the required size of the neural network that is required for like getting this capacity is not well understood. So for example, for ReLU networks, the best known result that we know of is that for one hidden layer network in the classical scalar regression setting, n data points can be memorized with n hidden nodes, which is, I think, not super surprising. But in this paper, we prove that for two hidden layer networks, root n dy neurons are sufficient for memorizing arbitrary and distinct data points, where dy is the output dimension. So we also show that in the case of dy equals 1, root n neurons are also necessary for memorization. So for example, this two hidden layer networks with two root n dy neurons per each hidden layer can memorize arbitrary n data points. So this means that only thousands of neurons are sufficient for memorizing millions of data points. And this also demonstrates depth-width trade-off in the setting of finite sample memorization, because by adding one more hidden layer, we can reduce the width requirement from n to root n. And we can also add extra depth to further improve the hidden node requirement, because in the case of multi-class classification with dy classes, this three hidden layer neural network with two root n, 4 dy hidden nodes can memorize arbitrary n data points. This, for example, means that ImageNet can be perfectly memorized with 2,000, 2,000, 4,000 neural net, hidden nodes. So this again demonstrates this depth-width trade-off in finite sample memorization setting. We also extend this result to deeper networks and show that the required width for perfect memorization scales inverse proportionally with the square root of L. And this network is actually a special case of the more general theorem statement that a network with W parameters in the hidden layers can memorize the data set if W is at least in the order of n. So in our paper, we define the memorization capacity as the maximum n such that the network can memorize arbitrary n data points in the case of dy equals 1. So the root n neurons can memorize the n data points result for this two hidden layer case gives a tight upper and lower bounds on the memorization capacity, which is theta of W. Again, W is the number of parameters in the hidden layers. And for L hidden layer case, the result that W equals omega of n is sufficient for memorization implies a lower bound on the memorization capacity, which is omega of W. And by definition of our memorization capacity, it's upper bounded by VC dimension, and there's a known upper bound on VC dimension, which shows that the VC dimension is upper bounded by WL and log W. So for any fixed L, our lower bound on memorization capacity W is almost tight. We have some other results as well on memorization in residual networks and SGD trajectory analysis near memorizing global minimum. So if you're interested in more details, please come to visit our poster. Thank you very much.
We're going to take like a maybe 4-minute break because we're a bit ahead of schedule because we're missing one spotlight. And a lot of people want to see the oral possibly. So I think, so at 4:25, we'll start the next oral. It'll be Andrew Cotter. But let's stay close.
To get rid of the stress that builds within me. I want to take off my clothes and hang from a tree. One day soon I will find. I know I am close. I know I will shine. One day soon I will fly. I know I am free. I'm feeling alive. Take me back to the jungle. Take me back to the jungle.
For anybody who's giving a spotlight in the second block, can you make sure that you're near the front and ready to line up after Andrew's talk? So the second oral of the session is going to be by Andrew Cotter on making stochastic classifiers deterministic.
Thanks. So I'm Andy. This is joint work with Hari and Maya. All three of us are at Google Research. So before I talk about converting stochastic classifiers into deterministic classifiers, I want to tell you why I at least care about stochastic classifiers. Now, stochastic classifiers arise in all sorts of applications. This is just sort of the motivating problem that caused us to start looking at this. And that's constraint optimization with data-dependent constraints. So for example, you might think about minimizing the error rate subject to some demographic parity constraints. Perhaps that for each protected class, you want to make the positive prediction rate at least 80% of the positive prediction rate of the overall population. There are many other things that can be written in this form. You can think about, having constraints that minimize churn. You can think about minimizing the false positive rate subject to false negative rate constraints, and so on. The thing that's going to be relevant for our purposes is that these constraints are non-convex. Now, because these constraints are non-convex, if we take sort of the obvious approach to optimizing this constraint problem, that is to say we write down the Lagrangian and we try to minimize the Lagrangian over the model parameters theta, and we try to maximize it over the Lagrange multipliers lambda, then because of the non-convexity of this problem, the Minimax theorem doesn't hold, and a pure Nash equilibrium might not even exist. That is to say there may not exist a theta lambda pair, which is a Nash equilibrium of the game being played between the theta and lambda players. However, under much more general conditions, a mixed equilibrium will exist. That is to say, there will be a distribution over thetas and a distribution over lambdas that's a mixed Nash equilibrium of this problem. And then that distribution over thetas, you can show, will give you a approximately feasible and approximately optimal solution to the original problem. One way to find this would be, say, to have the two players repeatedly play against each other, with the theta player playing best response, the lambda player playing gradient descent. They do this back and forth for a large number of iterations, and then if you take the uniform distribution over that sequence of iterates, that will be converging to a mixed Nash equilibrium of this problem. And then again, you take the uniform distribution over these thetas, and that gives you your stochastic classifier. You might think then, well, fine, we can make this a deterministic classifier by just averaging the thetas, taking the expected theta. But in fact, you can't, remember, because we don't have a convex problem here, we don't have Jensen's inequality, and we can't move the expectation from outside these GIs to inside these GIs. This is a problem that doesn't just show up in theory. In fact, we've run some experiments where we set up a constraint optimization problem, and we have the lambda and theta players run SGD against each other for a while, and that gives us this big, long sequence of iterates. Then we compare two things. One of these is the single best iterate that we observed throughout that entire sequence. The other thing is the single best distribution that's supported on that sequence of iterates. And we sometimes find a significant gap in the performance of these two classifiers in favor of the stochastic classifier. So it seems that perhaps a stochastic classifier is maybe not unavoidable, but at least is difficult to avoid in this problem, and the same is true in other settings as well. So while I sort of argued that stochastic classifiers are useful and perhaps sometimes unavoidable, there's a number of practical problems with them. Oftentimes in practical systems, you simply cannot use a stochastic classifier for a number of reasons. For example, as I mentioned on the previous slides, if you have a distribution over your entire sequence of iterates, that could be an extremely large object, very unwieldy to work with, compared to just a single model, a single set of thetas. Likewise, just sort of for more practical reasons, stochastic classifiers can be more difficult to debug and visualize, and even worse, in certain applications, a stochastic classifier might not just make sense at all. So I opened this talk by talking about a fairness problem with demographic parity constraints. There's many other notions of fairness one might be interested in. For example, Dwork et al. In their 2012 paper talked about a similar examples receive similar outcomes principle, where basically the idea is that if you have examples that are nearby in the feature space, you might consider them to be close to being indistinguishable, then it would be more fair to treat those examples equivalently than to treat them very differently. But a stochastic classifier really can't satisfy this property, right? Not only will similar examples perhaps receive similar outcomes, if you classify the same example repeatedly, you might get similar outcomes. There are different outcomes, I'm sorry. So to summarize, we prefer stochastic classifiers for performance reasons, but we prefer deterministic classifiers for practical reasons. And on this slide, I'm also introducing a little bit of notation. A stochastic classifier going forward will be written as a function without a hat, and it maps input instances to real numbers between 0 and 1, representing the probability of making a positive prediction. Deterministic classifiers will be written with hats, and they'll map input instances to either 0 or 1. And basically, as an outline of what we're going to do is, well, as you guessed from the title of the talk, we want to approximate a stochastic classifier with a deterministic one. And the first and most important question we have to answer once we start thinking about this is, what do we even mean by this? What does it mean to say that a deterministic classifier is a good approximation to a stochastic classifier? Once we've done that, we move on by saying, well, measured in these terms, is there some lower bound on how well a deterministic classifier can perform, how well it can approximate a stochastic classifier? Once we've proved that lower bound, we're going to move on and say, well, how well does the usual approach, that is to say thresholding the classifier at probability 1/2, how well does that perform? How does it compare to the lower bound? And we'll find that there's a pretty big gap there. And then finally, we're going to show that you can get closer to that lower bound using another fairly simple to implement procedure. So the first question we have to answer is, what constitutes a good approximation? Now, it should be fairly clear that you're not going to be able to approximate a stochastic classifier with a deterministic classifier pointwise. What we're going to do instead is sort of take a wide-angle view. We're going to ask the deterministic classifier to perform similarly to the stochastic classifier in aggregate across large swaths of the data set. To do this, we're going to define what we call metrics, and basically a metric consists of a loss, a labeling, and a subset of the data distribution. So for example, the example I talked about on the first slide, where we were minimizing error rate subject to a demographic parity constraint, the metrics of interest would presumably include the error rate, the positive prediction rate on the entire data set, and also the positive prediction rate for each of the protected classes. Now those protected classes would be the subsets of the data distribution, and that's something that is fairly important in our paper, but I'm going to ignore that for the rest of this talk because it sort of complicates things unnecessarily. So there will be no subsets going forward. And then the basic idea is that given M metrics, which we presumably chose based on the underlying problem of interest, we're going to ask our deterministic classifier to have similar performance to the stochastic classifier. So the first thing we do is show a lower bound. This is basically an elementary, almost trivial result. That if we're given a stochastic classifier F and we're given a data distribution, then there exists a metric and a labeling such that for every deterministic classifier, it will make an error of at least this quantity shown here on the slide, which is a max over all the points in our space of the probability mass on that point times a measure of the stochasticity on that point. Sort of the upshot of this is that if there is a large point mass and the stochastic classifier has a lot of stochasticity on that point mass, then we won't be able to find a good deterministic approximation. And that's fairly intuitive, I think. So I'm going to move this lower bound up to the top of the slide so we can compare to it moving forward. So probably the most obvious approach for converting a stochastic classifier to deterministic one is thresholding. What we're going to do is we're going to say that f hat makes a positive prediction if our stochastic classifier makes a positive prediction more than half of the time. And just sort of as a visual aid, you can think of this as kind of like converting a grayscale image to a black and white image by thresholding. And here again, this is a fairly straightforward result. We can show that given a stochastic f and a data distribution, for any metric and labeling, the error of this thresholded deterministic classifier will be at most basically an expected measure of the amount of stochasticity in your classifier. The important thing about this is that this bound improves as the stochastic classifier becomes less stochastic. That is to say, it's easier to deterministically approximate a nearly deterministic classifier. But unlike our lower bound, this bound does not improve as point masses shrink. And this is not a problem just with the lower bound, it's a problem with the approach itself. You can imagine if you have a continuous data distribution, so there's no point masses at all, our lower bound will be 0. However, if our stochastic classifier always makes a positive prediction 51% of the time, our deterministic classifier will always make a positive prediction, and there's this 49% gap in performance between the two. So we'd like to improve upon that. And to do so, we're going to look at this idea of hashing, which sort of comes from folklore. The idea here is that we're going to have a pairwise independent family of hash functions, and we're going to sample one of those hash functions. Once we've done so, we will use this hash function to define a deterministic classifier by every time we see a feature vector, an input instance, we're going to hash its features, and we're going to use that to give us a pseudo-random number that's kind of uniform in the range 0 to 1. And then that will be the threshold that we will use for this particular x. There will be a different threshold used for each x coming from this kind of pseudo-random hashed number. You can think of this as if the previous example of thresholding was converting a grayscale image to a black and white image by thresholding, this is maybe a little bit more like dithering. And remember, our goal is to try to look good from a wide angle view, not necessarily look good on each individual pixel or each individual example. Now, the bound that we prove here, this is actually a simplified version of the bound we have in our paper. But the bound we have here is, well, given here. We assume that we have a hash function with k buckets, and we have m metrics. And then with probability 1 minus delta over the sampling of the hash function, we can show that the error of the hashing classifier is going to be upper bounded by basically these two terms. The first term is something we can sort of ignore because we can choose the number of hash buckets, so we can make that first term go to 0. The second term you see is a min of two quantities, and the first of those quantities sort of measures the size of the point masses, and the second quantity sort of measures the amount of stochasticity in the classifier. This doesn't quite match the lower bound, but it has the same essential properties, namely that as the classifier becomes less and less stochastic, the deterministic approximation will be better, and also as the data distribution becomes more and more continuous, the deterministic approximation will become better. However, there's a number of drawbacks to this approach. The first is that, sort of as you might have seen from the dithering picture on the previous slide, will vary very widely even on nearby points. We won't really satisfy the similar examples yield similar outcomes property that I talked about on an earlier slide. It can be very non-smooth. In a sense, it's replacing stochasticity with arbitrariness. It's making arbitrary distinctions between similar examples based just on these hash functions. And so it has similar visualization and debugging and other practical problems as a stochastic classifier. So we might ask, well, what can we do to try to alleviate this a little bit? And one idea, and by no means is it the only one, I think this is something that can definitely be improved upon, is to think about interpolating between thresholding and hashing. So remember that thresholding, we're choosing the same threshold for every x. It's always 1/2. For hashing, we're choosing a different threshold for every x based on this hash function. What you can think about doing is instead partitioning your space in some way that respects similarity, that puts similar examples in the same partition element, and then choosing a different threshold for each partition element. This will wind up giving us the same bound on hashing, except that point masses will be measured on partition elements instead of being measured on individual examples. However, at least locally within each partition element, we'll have a similar example to receive similar outcomes property. So I'm going to close with a couple of simple experiments. Both of these are constraint optimization problems. In this one, the goal is sort of a fairness problem on the law school data set. We're trying to align two ROC curves. In particular, we're choosing a bunch of key points along the ROC curve, and we're saying that the ROC curve for the overall population should be similar to the ROC curve for the protected class. And we can see that if we optimize this without constraints, there's a pretty big gap between the two ROC curves. If we run SGD for a very, very long time and then choose the best distribution supported on the sequence of iterates, the two ROC curves are very close. Our approach works. The constraint optimization works. If, and here if you look on the rightmost plot, if we choose the best iterate instead of the best distribution, the gap returns again, so it doesn't work very well. And then in the middle plot, thresholding doesn't work very well. However, the second to the rightmost plot, hashing, the two ROC curves are very close to each other. The next example is on the adult data set. Here it's a histogram matching task, where instead of matching together points on the ROC curve, we're matching together points on a histogram. And in this case, again, the protected class histogram and the overall population histogram are very, very different for the unconstrained classifier. It works well for the stochastic classifier. Here, we don't plot the thresholding classifier. Instead, we plot the average classifier. This shows what happens if you just sort of take the expected theta and hope the Anson's inequality is true, which in this case it isn't because the constraints are non-convex. Overall, it appears that the hashing classifier performs much better. So thank you, and we'll be at poster number 231.
All right, thanks. Are there any questions for Andrew? Yeah. So while you're thinking, oh yeah, good. Yeah.
Can you just explain to me what the constraints would look like in these problems?
So for this, you might think about minimizing the maximum error between the two false positive rates at a number of false negative rate thresholds, or something like that. Does that make sense? We'd pick a bunch of false negative rates along the horizontal axis here, and then we'd constrain the false positive rates to be similar at those thresholded false negative rates.
Okay, so that's the minimax problem, and then the constraint that gets turned into a constraint problem where you're sort of having these constraints that ask them to be the same at every point or something?
Not quite the same. There's a couple of approaches you could take. Maybe the simplest thing to do would be just to say that we're going to minimize the maximum difference in the false positive rates at these false negative rate thresholds. So we'd introduce an extra variable representing the threshold at which the classifier is evaluated. And we'd optimize over that variable as well. It would sort of be included in our theta vector. And then for a number of such thresholds, we would then add constraints that the false negative rates at this threshold should be whatever we have on the horizontal axis. And then we'd evaluate the false positive rate at that thresholded classifier at that threshold and add a constraint that they should be similar. It's sort of, it's kind of an indirect approach. Does that? We had some auxiliary variables. And
it's a little clear, but I'm not super familiar with this stuff anyways, but I won't ask you to try and explain more right now. Thanks.
If you come to our poster, I'd be happy.
Yeah, thanks.
Thank you.
All right. Thanks. I forgot to mention, can all the Spotlight presenters please line up? So I think we're... So we're now going to have a sequence of Spotlight presentations. Without questions, you can take them offline. And if you're the second Spotlight presenter, please come up.
Hi, everyone. I'll be talking about our paper, Cold Case, The Lost MNIST Digits, which was joint work with Leon Boteau at Facebook and NYU. So everyone knows about the MNIST dataset, but what everyone does not know is that MNIST was created from a very large database called NIST. And MNIST was basically sampled from NIST. And it originally had 60,000 testing digits in the testing set, but 50,000 were chopped off because computers were slow at that time. And all the information on how we went from NIST to MNIST is just these two paragraphs that we can find in this paper. We don't know anything other than what is mentioned here about how MNIST's digits were sampled, or they were centered, or they were cropped, and so on. So initially when we wanted to reconstruct MNIST, we wanted to do it because we wanted to match digits with their metadata, like who wrote the digit, in which partition was it, and so on. As a side product of doing this reconstruction, we also managed to get the lost 50,000 digits. The first version of this dataset, of the reconstructed dataset, was created using the paragraph that we saw here, plus some old code in Lush database. And after that, the process was a back and forth between matching algorithms and fine-tuning our reconstruction algorithms. So here you can see some digits from MNIST and QMNIST. The new reconstructed dataset is called QMNIST. So you see the digits are very similar. You can't even tell which one comes from MNIST and which comes from QMNIST. So why should one use QMNIST? As you would have guessed, QMNIST testing set has 60,000 samples, which is 6 times of that what we have in MNIST. And we also have metadata like the writer ID, the partition ID, and so on. You can download it from the link that is given here, and it's very simple to use, just like MNIST. So the second half of the paper is about overfitting on MNIST. So if you keep using a standard data set for a long period of time, like MNIST has been used for 25 years, there's a huge chance that you overfit it, just like the leaderboard effect that we see in competitions like Kaggle. So since MNIST is small, the concern is even more so. And now you note that we have 50,000 new samples. So what we can do is we can re-implement previous models and then test them on these new 50,000 samples. So we tested on a lot of different algorithms. This one is for a simple feed-forward neural network. We changed the hidden unit size. This plots the test error percentage with respect to the hidden sizes. The thing in red is the test error with normal MNIST, and in blue is the error with reconstructed QMNIST analogous of the MNIST 10K. So you can see that they are very similar. So this hints about closed reconstruction. And the ones in green are on the new 50,000 samples that were never seen. So as you can see, the test error is higher, which hints towards a possible overfitting. This is a plot of all the experiments that we did. And as you can see, the errors on QMNIST 50,000 new samples is always higher. But the good thing to note is the classifier ordering always remains consistent. And the bottommost point in blue is for the best classifier on QMNIST, which is also the best classifier on the QMNIST 50K. So the conclusion is this phenomena that we call testing set rot, which occurs when you keep using a standard data set over a long period of time, it is real and it exists. But the good thing is that the classifier ordering remains consistent, and hence this phenomena is not as dangerous as we thought it was. And in reality, in real life, we should think more about distribution shifts, which can lead to worse performance than this phenomena. And this phenomena was also observed on Sapphire and ImageNet, but we do it in a more controlled setup. If you'd like to more and you have questions, please come to my poster, number 123, right afterwards. Thank you.
All right, as is custom, we're missing one spotlight presenter. It's either Akshay, Shai, Yoav, or let's see, are any of the presenters from the second spotlight here? Okay, if not, so let's continue with the next one. So, let's click through.
So hi everyone, my name is Aditya, and this is joint work with my colleagues at Google New York. So our paper is about multi-label learning. This is a fairly common problem where you're given an instance, for example, a video, and you'd like to predict a vector of binary labels. So for example, whether several categories are relevant for that video. So slightly more formally, I might have as input some pair of features x and a label vector y. So y, for example, could be a binary vector of some length L. And I'd like to produce some predictions f, which assign a real number to each of the L labels. And intuitively, at least, what I'd like is for the scores of the positive labels to be higher than the rest. Okay? Now, to achieve this goal, there have been a number of algorithms proposed in the literature. Our interest in this paper is in reduction-based approaches, of which maybe the most simplest and classical is what's known as the one versus all reduction. So here, basically, I just treat the problem as a sequence of independent binary classification tasks. Right? So I've got this complex label vector, but I just create a sequence of binary classification examples for each of the L labels. And now I just train a binary classifier on each of them separately. So very simple, very conceptually appealing. But of course, I'm not kind of capturing any correlations amongst the labels here. If I want to be a little more cognizant of that, I might do the following variant where I just take the positive labels and I create now a multi-class example for each of them. And as before, kind of train a classifier on each of these multi-class examples. So now just by the nature of a multi-class class, each of these individual components is actually going to take into account all the labels when you're making a prediction. So there are a few other reductions that are in the literature. All told, this gives us a landscape of different multi-label learning algorithms. There's a lot to like about these approaches. So they are leveraging very established, mature techniques from binary and multi-class classification. And just conceptually, they're very easy to reason about and seem quite intuitive. So this is all great. What we're interested in this paper is a slightly more fundamental conceptual question, which is what exactly are these different algorithms, different reductions optimizing, right? Just to be a little bit more precise, what multi-label performance measure am I actually optimizing if I'm choosing between one or more of these reductions, right? To get a handle on this question, it's useful to try and compare these different reductions on an equal footing. To do that, what I could do is say, let's pick one of these reductions, for example, the one versus all. Now, implicitly under the hood, this is minimizing some kind of multi-label loss. So I can imagine, for example, that the one versus all is minimizing a multi-label loss, which just so happens to decompose into a sum of binary classification losses. And similarly, I can do the same kind of analysis for the multi-class reduction. Here, the multi-label loss just so happens to decompose into a sum of multi-class losses on the positive labels. So now a loss function is kind of pushing me towards some target solution. So now each of the reductions has a corresponding loss function. So I can figure out for each of these reductions what exactly am I being pushed towards when I use this reduction. So we can work this out and we can go over the details at the poster, but basically it turns out that these reductions in general have subtle differences in terms of what they're actually optimizing. So the target that we're converging towards is slightly different for these reductions. This tells us, for example, something about the potential lack of calibration of probability estimates across different data points if you use a multi-class reduction. And so this is by itself, giving us some insight as to potential differences between these approaches. That's interesting. It's not quite answering the original question of what multi-label performance measure are we optimizing with these different approaches. So we are specifically interested in this question for retrieval settings. So here I have a budget, k, on the number of labels I'm allowed to predict. So for example, if k was 3, I'm only allowed to predict 3 labels as my prediction. So what I might do is take the top 3 highest scoring indices in my prediction vector f and look at the corresponding binary labels and just count how many of them happen to be positive. If I divide that by k, the budget, I get what's known as the precision at k. Whereas if I divide that by the total number of positives, which is in this case 5, I get what's known as the recall at k. So our basic finding is that just by the structure of the optimal solutions for these different reductions, it turns out that implicitly each of these reductions is actually optimizing for either the precision or the recall at k. Right? And in general, there's kind of a fundamental incompatibility between these measures, so you can't actually have a reduction that's directly optimizing for both at the same time. So that's our paper in a nutshell, and happy to talk more at the poster. Thanks.
I'm Margot Seltzer, and I'm delighted to present my work with Cynthia Rudin at Duke and her student Ziyang Hu, who's now at Carnegie Mellon. So what are we going to talk about with respect to decision trees? Decision trees have been around forever. They're old as dirt. And since the 80s or 90s, we've had standard methods like CART and C4.5 in building reasonably well-performing decision trees. But decision trees produced by these heuristic methods have 2 potential problems. One is that you don't actually know how close to optimal these models are. And the second is that if you start to build the model and happen to get a bad node at the root, you can produce models that are actually quite far away from optimal. So why don't we just search the entire space of decision trees and find the best model? And the answer is because the space is prohibitively large. So for real problems, you're talking about space on the order of 10 to the 28. So how on earth can we find an optimal decision tree given that size search space? And the answer is that what we need to do is we need to figure out ways to effectively prune the search space. And if we could prune the search space such that we find what is actually the best model or the needle in the haystack, not only can we give you the best model, but we can give you a certificate that says, given the data set you gave me to train on, this is in fact the best model you can do. And so that's what we're doing. The way we're going to do this is we're going to solve an optimization problem. So what we want to do is minimize a regularized loss function where the loss did not render on the PDF, but it's basically the misclassification error across all the leaves in the tree. And then we're going to regularize by a sparsity function that's going to favor trees with fewer leaves. Fewer leaves means we're not going to overgeneralize. I'm sorry, we are going to generalize and we aren't going to overfit. So for example, in the well-worn COMPASS data set from the Broward County recidivism data, this is in fact the optimal tree on the training data. What you'll notice is it's not a particularly pretty tree. It's not balanced, it's not perfect. Some of the leaves are at level 4, some are at level 1, but it does in fact generalize well and give you as good accuracy as anything else. So how do we do this? We're going to search the space using a branch and bound algorithm. We're going to use a good scheduling order in how we search that space. And then we're going to aggressively apply mathematical bounds to the loss function so that we can prune off large portions of the space. We'll keep track of incremental computation so that we'll keep track of the computation we've done so that we can perform incremental computation as the algorithm progresses. And the result is that the algorithm is fast. So what I'm showing you is the time the algorithm runs on the compass data set. At the top, what you see on the x-axis is the number of samples in the data set. And in blue, it's the total time until we give you the certificate of optimality. And in black, it's the time it took to find that optimal solution, not knowing it was the optimal. So the good news in the top picture is that we actually scale linearly in the number of samples. The interesting news in the bottom picture is that if we do this as a function of the number of features in the data, we scale very well to find the actual optimal solution, but we scale exponentially, as you might expect, to be able to prove that the solution is in fact optimal. In addition to being fast, as you would expect, the models are accurate. So on the tic-tac-toe data set on the top, in gold, you have our optimal sparse decision trees. In purple, you see CART. And in blue, you see BinOct, which is a modern other approach to optimality, which requires that the trees be perfect, full, balanced trees. And so what you see is on tic-tac-toe, we actually we produce more accurate models. At the bottom, you see the compass data, and we produce comparably accurate models, but we do so with many fewer features. How do we do this? A whole bunch of bounds, which I can talk about at the poster session. Some of the more important ones, because we're regularizing the loss function, if a leaf doesn't have enough points described by it, then it's never going to be in the optimal tree, and we can prune. Similarly, even if the node has enough points, but they're not accurate, it's never going to be in the optimal tree, and we'll prune it. You can represent a tree by its collection of leaves. And so if you find multiple trees that have the same number of leaves, the identical leaves, they're the same tree, and you can throw them away. So lots of other bounds. We're at poster number 15. The code is available. You can download it and play with it. And it's both fast, accurate, and interpretable.
Okay, yeah. I'm Nishant Mehta, your session chair, and this concludes the session and is the beginning of the poster session. Thanks.